What if the key to humanity's future in space wasn't just about surviving the harsh conditions, but truly thriving among the stars? Imagine stepping onto a space station where the ground feels as solid beneath your feet as it does on Earth. This isn't science fiction, it's the promise of artificial gravity. Today, we're unraveling how this revolutionary concept could transform the dream of long-term space habitation into reality. From the science behind gravitational forces to the challenges that lie ahead, and the innovations that push the boundaries of what's possible, we'll explore how artificial gravity might just be the next giant leap for mankind's journey into the cosmos. The quest for artificial gravity in space has intrigued minds for centuries, weaving through the fabric of both scientific inquiry and speculative fiction. From the imaginative prose of early visionaries to the rigorous pursuits of modern-day researchers, this concept has been a beacon of hope for expanding humanity's reach beyond our terrestrial home. Let's journey through history to see how this intriguing idea evolved and laid the groundwork for the revolutionary designs we explore today. In the pages of early science fiction, luminaries such as Jules Verne and H.G. Wells introduced readers to worlds where humanity had conquered the stars, often hinting at the need for gravity-like forces to make such existence feasible. These narratives didn't merely entertain, they inspired generations to consider how artificial gravity could be achieved. The allure of centrifugal force, a rotating space habitat where the outer walls serve as ground due to centripetal acceleration, emerged as a recurring theme, threading through the literature and inspiring real-world scientific discourse. Fast forward to the mid-20th century, when scientific pioneers began to morph fiction into preliminary blueprints. Visionaries like John Desmond Bernal proposed the Bernal sphere, a rotating space habitat concept developed in the 1920s. This colossal structure aimed to mimic Earth's gravitational pull through rotation, providing a livable space environment for its inhabitants. Decades later, in the 1970s, physicist Gerard K. O'Neill expanded on these ideas with the O'Neill cylinder. His vision was a pair of counter-rotating cylindrical colonies, each the size of a small city, designed to provide not only gravity but also a full ecosystem capable of supporting human life. Although these imaginative constructs never materialized, they profoundly influenced how we think about living beyond our planet's borders. They demonstrated that creating artificial gravity wasn't just a flight of fancy, it was a necessary step towards sustainable space colonization. The technologies these designs envisioned have informed our understanding of space habitat construction, environmental systems, and the physical requirements of long-term human life in orbit. While none of these early concepts have been realized in their entirety, they have served as critical inspiration for contemporary advances in space architecture. Today, researchers and engineers are turning these pioneering visions into actionable technologies. Rotational space habitats remain a significant area of interest. Modern initiatives are exploring smaller, modular versions of these designs, balancing the technological limitations of our era with the ambitions of those early schemes. The pursuit of artificial gravity is not without challenges: engineering limitations, material constraints, and the sheer scale of such projects present significant hurdles. However, the drive to overcome these obstacles is fueled by the understanding that gravity is essential for health and well-being in space. Prolonged exposure to microgravity can lead to severe health issues, including muscle atrophy and bone loss, underscoring why artificial gravity isn't just an enhancement but a necessity. As we transition from historical concepts to current advancements, it's essential to recognize the lessons we've gleaned from those bold, early ideas. They remind us to think big, to remain undeterred by the boundaries of current technology, and to envision a future where humans can live and thrive throughout the cosmos. This blend of imagination and scientific rigor continues to guide the ongoing quest to bring the dream of artificial gravity from the realm of fiction into the tangible reality of space exploration. As we delve into the present landscape of artificial gravity technology, it's fascinating to witness how science fiction dreams are slowly becoming scientific reality. The cornerstone of this emerging field lies in the understanding and application of fundamental physics principles, particularly centrifugal force. This force, experienced when an object moves in a circular path, is central to creating an artificial gravitational effect in space. Let's start with rotational habitats where centrifugal force plays a starring role. Imagine a giant spinning wheel in space. As it rotates, everything inside is pushed outward, similar to how we feel pressed into our car seats when taking a sharp turn. This rotation creates an effect akin to gravity, where those aboard can walk on the inner surface of the wheel as if it were solid ground. The faster the rotation, the stronger the gravitational pull. Researchers at NASA and other space agencies are actively exploring this concept with ambitious designs. These include rotating modules either attached to existing spacecraft or as standalone structures, with the goal of achieving a balance between sufficient gravity and comfort for human inhabitants. A specific project that has garnered attention is NAS, a concept for an artificial gravity treadmill. Here, astronauts would exercise in a rotating environment that simulates gravity, thereby mitigating muscle atrophy and bone loss during long missions. This experimental approach not only aims to improve astronaut health, but also serves as a step towards understanding the viability of larger-scale rotating habitats. Beyond rotational systems, tether-based solutions offer another intriguing possibility. Picture two spacecraft connected by a tether, spinning around a common center of mass. This method also utilizes centrifugal force, creating a gravity-like experience along the tether's length. One such notable experiment is the European Space Agency's proposal for a tethered habitat. By deploying a counterweight system, this technique could offer artificial gravity in rotating sections of the spacecraft. The European Space Agency's studies in this area, along with collaborative efforts with NASA, underscore the international commitment to unlocking the potential of artificial gravity. These agencies are not only testing theories on paper, but are also developing detailed prototypes and simulations. These efforts are crucial as they help address the practical challenges of building and deploying these systems, such as ensuring structural integrity in the hostile environment of space. However, the road from concept to reality is fraught with challenges. The sheer scale of building large rotating structures in space poses significant engineering hurdles, from material limitations to energy requirements. Moreover, there are concerns over the potential impacts of rotational forces on the human body, particularly the vestibular system, which helps regulate balance and spatial orientation. These factors are critical as they determine how artificial gravity might affect astronauts over extended periods. Despite these obstacles, the opportunities that artificial gravity offers are immense. Successfully implementing such systems could revolutionize long-term space habitation, potentially making missions to Mars or beyond more feasible by providing a semblance of Earth-like living conditions. It could also pave the way for space tourism, with stations that offer a more comfortable experience for travelers unaccustomed to weightlessness. As we continue to learn from pioneering experiments and refine these technologies, the possibility of living and working in artificial gravity environments becomes increasingly real. It's a thrilling time in the exploration of space, where each breakthrough brings us a step closer to realizing the dream of not just surviving, but thriving in the cosmos. The collaboration between agencies like NASA and ESA ensures that we're pooling the best of human ingenuity to tackle the complexities of this frontier, turning the dream of artificial gravity into a tangible element of future space missions. In the stark and unforgiving environment of space, one of the most significant challenges facing astronauts is the physiological toll of prolonged weightlessness. On Earth, gravity is a constant force acting upon our bodies, shaping everything from muscle development to bone density. But in the microgravity of space, these forces vanish, leading to profound changes in the human body. Muscle atrophy and bone density loss are among the most critical issues, posing risks not only to the health of astronauts, but also to the success of long-duration missions. Muscle atrophy occurs because our muscles, particularly those in the legs and back, no longer bear the weight they do on Earth. In microgravity, the body quickly adapts by reducing muscle mass and strength, a process that can begin within days of entering space. Without the constant resistance provided by Earth's gravity, astronauts can lose up to 20% of their muscle mass within a few weeks. This weakening of muscles can impair movement and coordination, both of which are essential for performing tasks during missions. Bone density loss is another significant concern. Our bones continuously undergo a process called remodeling, which balances the breakdown of old bone with the formation of new bone. This process is heavily influenced by the mechanical stresses placed on them by gravity. In space, the absence of these stresses leads to an acceleration in bone resorption compared to bone formation, resulting in a net loss of bone mass. This can lead to osteoporosis-like conditions, increasing the risk of fractures not just in space but also upon return to Earth. Enter artificial gravity, a promising solution to these biological challenges. By simulating the effects of Earth's gravity through rotational forces, artificial gravity aims to provide the necessary mechanical stresses to maintain muscle and bone health. This could essentially trick the body into thinking it is still under the influence of Earth's gravity, thereby preserving muscle mass and bone density. The concept of integrating artificial gravity into space habitats is gaining traction. Rotational habitats, such as rotating rings or wheels, could create a stable environment where astronauts can live and work with reduced risk of physiological decline. These environments would allow for a more Earth-like experience, where walking, exercising, and performing daily activities generate the gravitational resistance needed to preserve muscle and bone health. Moreover, incorporating artificial gravity into space missions could enhance overall health and performance. By mitigating the detrimental effects of microgravity, astronauts could maintain better physical fitness, which is crucial for the demanding tasks required during space travel, such as repairs, scientific experiments, and exploratory missions. Better health means a reduced need for medical intervention, lower risk of injury, and more successful mission outcomes. Research into artificial gravity is not just theoretical. Experimental studies with centrifuges and rotating platforms have been conducted to evaluate their effectiveness in combating muscle and bone loss. These studies inform the design of future space habitats, ensuring that the integration of artificial gravity is both practical and beneficial. Additionally, the psychological benefits of having a gravitational environment similar to that of Earth cannot be overstated. The sensation of walking or having a defined up and down can provide significant mental comfort, reducing the cognitive load and stress associated with long-term space missions. Incorporating artificial gravity into space habitats represents a significant step forward in overcoming the biological challenges of space travel. By addressing the root causes of muscle atrophy and bone density loss, these solutions promise to enhance the health, safety, and effectiveness of astronauts, ushering in a new era of human space exploration where thriving, not just surviving, is the ultimate goal. As we venture further into the cosmos, innovative designs are paving the way for a new era in space habitation where artificial gravity is no longer a distant dream but a tangible reality. Engineers and architects are pushing the boundaries of what's possible, unveiling groundbreaking concepts and prototypes that harness creativity and technological prowess. Among these, the designs of toroidal and cylindrical space stations, virtual reality simulations, and centrifuge modules stand out, each offering a unique approach to integrating artificial gravity into space habitats. Toroidal space stations, reminiscent of a giant spinning donut, leverage rotation to create a gravitational effect along their curved surfaces. This design concept isn't new. It traces back to visionaries like Wernher von Braun, who envisioned such structures as early as the mid-20th century. However, with today's advancements in materials science and aerospace engineering, these toroidal structures are becoming more feasible. They promise to provide a stable environment where astronauts can walk, eat, and conduct experiments in conditions similar to Earth, reducing the health risks associated with long-term exposure to microgravity. Cylindrical space stations, on the other hand, offer a different twist on the same principle. These designs, often referred to as O'Neill cylinders, comprise large rotating habitats that might house entire communities. The concept involves spinning vast cylindrical structures to generate centrifugal force, simulating gravity on the inner surface of the cylinder. Modern advancements make these designs more than just theoretical. Engineers are considering the structural integrity, energy efficiency, and sustainability of these habitats, making them blueprints for potential future colonies on the Moon or Mars. Beyond physical prototypes, virtual reality (VR) simulations play a crucial role in this architectural revolution. By creating immersive environments where astronauts can experience and train for life in simulated artificial gravity settings, VR technologies bridge the gap between design and reality. These simulations are essential for testing how humans might interact with these novel spaces, allowing designers to refine their ideas and anticipate challenges before constructing actual habitats. Then there are centrifuge modules designed to function as part of larger spacecraft or space stations. These modules rotate independently, creating pockets of artificial gravity where astronauts can spend parts of their day. This modular approach is particularly appealing because it doesn't require an entire habitat to rotate, offering flexibility in design and operation. It also allows for gradual integration into existing space structures, making the transition to artificial gravity more seamless. While these designs are currently in various stages of development, they represent a significant step forward in how we think about living in space. The transition from design to reality is a delicate process involving rigorous testing, innovation in materials and construction methods, and collaboration across international agencies. But as these prototypes are refined and tested, they could influence future missions by providing safer, more comfortable, and sustainable living conditions for astronauts on extended journeys. Moreover, these innovative designs offer more than just practical benefits. They inspire a new vision of human life beyond Earth. They challenge us to think differently about space habitation, not as a temporary expedition, but as a step towards becoming an interplanetary species. Such advancements could open doors for space tourism, long-term scientific research, and even the preservation of human culture and biodiversity, making space not just a destination but a new frontier for human civilization. As we continue to explore and develop these concepts, the day when artificial gravity becomes a standard feature of space travel may not be far off. By daring to dream and innovate, we are crafting the future of life in space, turning the once far-fetched fantasy of living among the stars into a future reality. This journey is a testament to human ingenuity and our relentless pursuit of knowledge and adventure, promising a thrilling chapter in the story of human exploration. While the allure of artificial gravity in space captivates our imaginations and holds the promise of transforming human space habitation, we must consider the economic realities that accompany these lofty ambitions. Implementing artificial gravity systems isn't solely a technical endeavor. It represents a significant financial undertaking, one that requires innovative economic strategies and models to become viable. Let's explore how current economic factors and financial models are shaping the future of artificial gravity in space, and how these could support a burgeoning industry of space tourism and habitation. First, we must address the substantial costs involved in developing and maintaining artificial gravity systems. Creating rotational habitats or centrifuge modules requires cutting-edge materials, advanced engineering, and significant time investment. These factors drive up the initial capital required for research, development, and deployment. Moreover, ongoing maintenance and operational expenses present additional financial challenges that must be met to ensure the long-term usability and safety of these space habitats. Despite these challenges, the potential economic impact is immense. The growing interest in space tourism represents a lucrative market that could fund and justify the initial investment in artificial gravity technology. Companies like SpaceX and Blue Origin are already paving the way with their aspirations to make space travel accessible to the public. Artificial gravity could enhance these experiences by offering comfort and reducing the health risks associated with prolonged weightlessness, thereby making space tourism more attractive to a broader audience. To support such ventures, emerging financial models are being developed. Public-private partnerships, for instance, combine the resources and expertise of governmental agencies with the innovation and efficiency of private companies. This collaborative approach helps distribute the financial risk and encourages investment in space infrastructure, including habitats with artificial gravity. Another promising model is the concept of scalable modules. By developing modular space systems that can be expanded or replicated, companies can initially launch smaller, cost-effective versions of artificial gravity habitats. As technology advances and costs decrease, these modules can be scaled up or adapted for different purposes, such as scientific research, industrial manufacturing, or residential habitats, thereby increasing their commercial potential. Additionally, the prospect of space resources such as mining asteroids for rare minerals or manufacturing in microgravity environments could provide new revenue streams. Artificial gravity systems can support these activities by providing stable environments where humans can live and work effectively. The revenue generated from these ventures could, in turn, offset the costs of developing and maintaining artificial gravity, creating a sustainable economic cycle. The economic viability of artificial gravity also hinges on the scalability of these technologies. As we refine and reduce the costs of building and launching space habitats, we open the door to more accessible and frequent space ventures. This scalability is crucial for transitioning artificial gravity systems from niche technological novelties to integral components of the everyday space experience. In conclusion, while the financial challenges of implementing artificial gravity in space are formidable, the potential rewards are equally substantial. The market for commercial space tourism and habitation is growing, driven by technological advancements and decreasing launch costs. By embracing innovative financial models and focusing on scalability, we can overcome the economic hurdles and usher in a new era where artificial gravity is not just a possibility but a commercially viable reality. As we continue to innovate and collaborate, we set the stage for sustainable space ventures that could redefine our relationship with the cosmos, making space not just a destination for exploration, but also for living, working, and thriving. In the grand narrative of human space exploration, a manned mission to Mars stands as a pinnacle of ambition and innovation. This endeavor, envisioned as a stepping stone to becoming a multi-planetary species, demands the confluence of cutting-edge technology, robust planning, and pioneering spirit. Among the myriad challenges presented by interplanetary travel, the role of artificial gravity emerges as a critical component in ensuring the mission's success. By examining this case study, we gain insights not only into the practical application of artificial gravity during the journey to Mars, but also its potential to redefine the future of interplanetary exploration. The journey from Earth to Mars is no small feat, a trip that could span several months, depending on orbital alignments and propulsion technology. During this prolonged transit, astronauts face significant health risks associated with extended exposure to microgravity, including muscle degeneration, bone density reduction, and cardiovascular deconditioning. Here, the integration of artificial gravity could provide a vital lifeline. Imagine a spacecraft designed with a rotating module, a compact toroidal section where centrifugal force simulates gravity. This environment would allow crew members to engage in daily routines, exercise, and rest in conditions that mimic Earth's gravitational pull, thereby mitigating the adverse health effects of prolonged weightlessness. But the advantages of artificial gravity extend beyond physical health. Such a system would contribute to the psychological well-being of the crew by providing a sense of normalcy and structure that is inherently aligned with human circadian rhythms. The ability to walk, experience a defined up and down, and perform everyday tasks could reduce stress and enhance cognitive function, essential factors for maintaining morale and performance during a demanding mission. Upon arrival at Mars, the challenge shifts from surviving the journey to establishing a sustainable presence on the Martian surface. Here, artificial gravity could again play a pivotal role. Martian gravity is roughly 1/3 of Earth's, which, while better than microgravity, still poses long-term health challenges. Hypothetical scenarios suggest the establishment of rotating habitation modules or centrifuge-equipped facilities within Martian colonies, providing zones where a more Earth-like gravity can aid in physical rehabilitation and long-term habitability. Moreover, the utilization of artificial gravity on Mars might serve broader scientific and operational purposes. Facilities equipped with adjustable gravity environments could become vital research hubs, allowing scientists to study the effects of varying gravitational forces on biological systems, materials science, and agricultural practices in space. This knowledge would be invaluable not just for sustaining Martian colonies, but for planning future missions to other celestial bodies. The implications for interplanetary travel are profound. By incorporating artificial gravity into the design of future spacecraft and extraterrestrial bases, we lay the foundation for safer, more efficient space missions. This technology can improve crew health and operational capability, making longer voyages to further destinations conceivable. Furthermore, it democratizes space travel, potentially extending stays and broadening participation beyond seasoned astronauts to include researchers, educators, and eventually civilians. In contemplating the Mars mission case study, we see artificial gravity not just as an enabler but as a catalyst for the next chapter of human exploration. It challenges us to rethink our technological approaches and prioritize human health and safety as we push further into the cosmos. As we continue to dream, plan, and build, artificial gravity stands as a testament to our capacity to overcome the constraints of physical law and time, bringing the dream of interplanetary living within reach. As Mars beckons, the journey toward an interstellar future, buoyed by the ingenuity of artificial gravity, propels us into an era of unprecedented exploration and discovery. As the frontiers of space exploration expand and artificial gravity becomes a more integral component of long-term space habitation, we find ourselves at the crossroads of progress and responsibility. While the technological possibilities are tantalizing, they usher in a host of legal and ethical considerations that we must navigate with care. These considerations are not merely footnotes in the grand scheme of space exploration. They are crucial elements that will shape the future governance of outer space and determine how we, as a species, respect and protect the lives of those venturing into the cosmos. Legally, space is governed by an intricate tapestry of international treaties and agreements, with the Outer Space Treaty of 1967 serving as the cornerstone. This treaty, ratified by over 100 countries, including major spacefaring nations, outlines the basic framework for space exploration. It emphasizes that outer space, including celestial bodies, is free for exploration and used by all states, but it must be done for the benefit of all humankind with a focus on peace and cooperation. However, as we move toward commercializing space travel and establishing artificial gravity habitats, existing legal frameworks will need to evolve. Who is responsible for the safety of individuals living on a space station with artificial gravity? How do we handle jurisdictional issues when these habitats involve multinational partnerships? These questions are at the heart of space law's evolution. As commercial entities play a growing role, there is a need for more specific legal standards that address liability, property rights, and the regulatory oversight of artificial gravity systems. The challenge lies in crafting regulations that ensure safety and fairness while fostering innovation and collaboration. National and international regulatory bodies will need to work closely to harmonize these rules, establishing clear guidelines that protect both investors and inhabitants. On the ethical front, the implementation of artificial gravity in space raises profound questions about human rights and well-being. Long-term space habitation requires careful consideration of inhabitants' physical and mental health. In artificial gravity environments, how do we ensure that every individual receives adequate health care, a comfortable living environment, and the freedom to return to Earth if desired? Moreover, as we establish habitats that mimic Earth-like gravity, we must consider the psychological impacts of separation from our home planet. The isolation and constraints of living in an artificial environment could have significant implications for mental health, requiring robust support systems and continuous monitoring. Ethical considerations also extend to the broader implications of colonizing other worlds. As we create artificial gravity habitats on places like Mars or in orbit, we must deliberate on our responsibilities to preserve these environments. Should these ventures prioritize scientific discovery and environmental stewardship over commercial gain? How do we balance the pursuit of knowledge against the potential for exploitation of celestial resources? Furthermore, the inclusion of diverse perspectives is essential in shaping the ethical framework for space habitation. As space becomes more accessible, ensuring that people from different cultures, backgrounds, and nationalities participate in these explorations will enrich our collective understanding and governance strategies. It's crucial that the benefits of space exploration are shared equitably among all of humanity, not just a select few. In conclusion, the development of artificial gravity technologies offers exciting opportunities for human expansion into space. Still, it simultaneously demands rigorous legal and ethical scrutiny. As we stand on the brink of this new era, it is our responsibility to forge a path that respects human rights, promotes safety, and ensures that the vastness of space becomes a domain of peace and shared progress. By thoughtfully addressing these legal and ethical implications now, we lay the groundwork for a sustainable and just future among the stars, ensuring that our cosmic endeavors reflect the highest ideals of humanity. As we peer into the future of space exploration, the trajectory of artificial gravity is poised to be both transformative and exhilarating. The advancements that lie ahead promise to redefine not only how we live in space, but also how we interact with the cosmos. At the heart of these innovations are autonomous habitats and artificial intelligence-driven systems, each pushing the boundaries of what's possible and ushering in a new era of human presence in space. Imagine a space habitat that functions much like a self-sustaining ecosystem, capable of autonomously maintaining its artificial gravity systems, environmental controls, and resource management. This vision is rapidly approaching reality as advances in robotics and automation make autonomous habitats increasingly feasible. These habitats could operate independently of Earth-based control for extended periods, adapting to the needs of their inhabitants and mitigating the risks associated with space living. One exciting development in this area is the use of smart materials and adaptive architecture. These technologies could allow habitats to dynamically alter their structural and functional properties in response to changing conditions or specific mission requirements. For example, a habitat might expand or contract its living quarters based on the number of occupants, or adjust its rotational speed to optimize the artificial gravity generated for different activities. Such adaptability would enhance the efficiency and comfort of living in space, making long-term space habitation more viable. Artificial intelligence plays a crucial role in these future trends. AI-driven systems can monitor and manage the complex operations within a space habitat, from life support and energy distribution to waste recycling and food production. By using machine learning algorithms, these systems can continuously improve their performance, learning from past data to predict and prevent potential issues before they arise. This predictive capability is essential in the high-stakes environment of space, where quick and effective decision-making can be the difference between success and failure. Moreover, AI-powered robotics could revolutionize construction and maintenance in space. Robotic systems equipped with AI could assemble habitats in orbit or on planetary surfaces, conducting repairs and upgrades autonomously. This would significantly reduce the need for human intervention in dangerous or labor-intensive tasks, allowing astronauts to focus on exploration and research. The integration of artificial gravity with these advanced technologies opens up new possibilities for the next generation of space exploration. For instance, autonomous habitats with artificial gravity could serve as way stations or research outposts on the Moon or Mars, supporting exploratory missions or serving as bases for further expeditions into the solar system. These outposts could facilitate the collection and analysis of extraterrestrial resources, contributing to the sustainable development of space environments. Furthermore, these advancements could make space tourism more accessible and enjoyable. With autonomous systems ensuring safety and comfort, tourists could experience space living with minimized risk, perhaps even enjoying Earth-like conditions during their stay. This could ignite a new industry, creating economic opportunities and generating public interest in space exploration. As we look to the future, the path ahead for artificial gravity is paved with potential. The combination of autonomous habitats, AI-driven systems, and adaptive technologies promises to revolutionize our approach to space living, making the dream of thriving in outer space a reality. These innovations not only enhance the feasibility of long-term missions, but also invite us to rethink our relationship with the cosmos. As we stand on the brink of this new era, the possibilities are as vast as space itself, offering endless opportunities for discovery, innovation, and progress. The future of artificial gravity is not just a technological frontier, it's a testament to humanity's enduring spirit of exploration and our ability to overcome the challenges of the unknown. Artificial gravity stands as more than just a fascinating scientific challenge. It embodies the indomitable spirit of human curiosity and our relentless drive to explore the great expanse beyond our home planet. As we've journeyed through the past and present of this groundbreaking technology, we've uncovered stories of visionary thinkers, examined the practical hurdles of creating gravitational environments in space, and glimpsed the thrilling innovations and future possibilities that lie ahead. This exploration not only expands our understanding of artificial gravity, but also reshapes our vision for space habitation, a vision where humans can not only survive but thrive in the vastness of space. Reflecting on these insights, we're reminded that our pursuit of artificial gravity is deeply intertwined with our aspirations for the future. It challenges us to rethink how we engineer our living spaces, maintain human health, and build sustainable societies beyond Earth. Each advancement in creating artificial gravity systems brings us a step closer to making long-term space colonization a reality, highlighting our innate desire to go beyond the known and our capacity to achieve the extraordinary. But this journey isn't just for the scientists and astronauts, it belongs to all of us. Each one of us has the potential to contribute to and be inspired by this cosmic endeavor. Whether through supporting space research, engaging in meaningful discussions about the future of space exploration, or simply dreaming about the possibilities that await us among the stars, there is a place for everyone in this unfolding story. Imagine the future we can build together, a future where space is not just a frontier for exploration but a vibrant realm of human presence. Picture a world where children grow up knowing that traveling to the Moon, Mars, or even further is not just a dream but a genuine possibility. Consider how our efforts today in developing artificial gravity and other space technologies can lead to groundbreaking discoveries that benefit all of humanity, from new scientific insights to innovations that enhance life on Earth. As we stand at the cusp of this new era, the potential of our cosmic journey is limitless. The challenges are significant, yet the rewards of overcoming them are far greater. They remind us that human ingenuity knows no bounds, and that with collaboration, perseverance, and imagination, we can transform the impossible into reality. So let's take this next step together. Let's embrace the unknown with open hearts and minds, encourage one another to push the limits of what we know, and boldly chart a path toward a future where space is a shared space for every one of us. Whether you're a budding scientist with dreams of contributing to space research, an avid enthusiast keen to learn and engage with the latest developments, or someone who simply stares up at the night sky with wonder, there's a role for you in this grand narrative. Join us on this journey of exploration and innovation. Let's continue to dream big, support one another, and shape a future where artificial gravity is not just science fiction but part of our everyday lives. Together, as one global community, we have the power to reach for the stars and build a new home among them.